Alright, hello Calc peeps. This is going to be really helpful for the individual work that y'all will be doing at home tonight, and even a lot of the group work, the group problems that I've assembled for y'all for today. Or, I mean, you might have already seen it or already done it, in which case this would have been really helpful. I hopefully will have let you know during class that this was something that you should have watched. But we're going to go over some intuitive notions of continuity. This is going off of the notes from 1.2.1, but I'm going to be really explicit with how I do this. So continuity just means that you can draw your function along the whole graph without ever, or along the coordinate plane without ever taking your pen off of the coordinate plane. So we're gonna, like it says in the description, we're gonna go over a more in-depth way of defining this idea of continuity in chapter 2, but this will be sufficient for our uses now. So we need to first look at an example f of x of being what is called a piecewise function. So a piecewise function means that our function changes rules after a certain point. So we show this with some braces that look like this. And for this specific case, we're going to look at two different parts to our function. One is going to be 9 minus 2 to the x power, and we're going to follow this rule for values where x is less than or equal to 3. So if we're at x equals 3, if we look to the left of this, or to the smaller values, it's going to follow this function right here. So when x equals 0, y is equal to 9. And finally, we get at 3, our value is 1. So we know that our function kind of looks like this, to the left. Just evaluated 2 points, knowing how this behaves in terms of that left side. We're going to wait for the noise to go away, and then we can continue. Okay, so for the next part of our piecewise function, we're actually going to follow a different rule when we go to the right of this boundary, or to values where x is greater than 3. So in this case, we're going to take the square root of x minus 2. And what that looks like, we kind of saw it before. It's going to look like that. So that's really all there is to drawing these piecewise functions, but notice that as I am tracing this, my pen never leaves the graph, my pen never leaves the coordinate plane to get to the next part. So this is actually going to be a continuous function. So let's take a look at another function that might not be continuous, but actually discontinuous. So that would be something like g of x, our function g of x being equal to 0.5 times x squared plus 1 for x values less than 4. So we're defining our boundary right here. X equals 4. And so that is actually going to be end right up here at 9. Or notice how I left it as an open dot. So the open dot is the strictly less than. If you fill in the dot, that's the equal to. So at x equals 4, there's a hole in here. We're not talking about this value anymore. We might be talking about the other function. So this thing will dip down and then go back up and go back to positive infinity in the x value. So our next function is going to be the next value for this function will be 1.5x. For x value greater than or equal to 4. So in this case, at x equals 4, we actually have a value of 6. And then it's just going to increase like so forever. So notice how, and I actually didn't do too great of a job of showing that vertical line, but notice how when I trace this, I have to take my pen off, jump back down to the 6 to continue on. So in this case, we are going to have a discontinuous function. Just means that there's a jump in the function, jump in the graph. So this is something we talked about during our graphing stories, or our function stories, but it's good to see it, an example of this with a piecewise function, a function that has different rules depending on where on your x-axis you are. One other thing I'd like to you to notice is that when it's greater than or equal to, that's when we fill it in. Same with less than or equal to. So open circle for strictly less or greater, filled in for less than or equal to or greater than or equal to. So there's a lot of functions that are continuous. I'm just going to list them off and give you some quick graphs. So polynomial functions, those are going to be any functions that kind of look like so. Usually they're going to have descending exponents that are whole numbers. Next up, we can have a rational number or rational function. So rational functions tend to be continuous too. And those are anytime we have fractions in our exponents. So those might look a little bit like this, or it might look like this. But notice how at all points it's very continuous. Power functions are also going to be continuous. So something like f of x equals 2 to the x power. And let's make it more interesting. We're going to add 3 to it. So 1, 2, 3. It's just going to look like that. So again, no jumps or skips. Logarithmic functions. Didn't quite make it to these last year, I don't think, but we will. So that could be something like y equals the log base 7 of x. And in general, these functions kind of take on this shape right here. Got two more, or actually one more. Big family. We have the trigonometric functions. You should be familiar with those from last class, or last year. Oh yeah, we're in calculus right now. You've totally seen logarithmic functions. Trigonometric functions we spent a bit of time doing last year too. So an example would be like y equals the sine of x. So we can graph that out and notice that it too is consistently continuous. Okay? So that's all there really is to continuous functions, piecewise functions. You're going to explore this in your lesson tomorrow. What I'm going to do for the next video is kind of talk about domain and range and how there's two different ways to do so, to represent them. So watch the next video. Hopefully everything will make sense in the individual work.